We're going to talk about space, the future of space. So going way back, I was in the military a long, long time ago, and we had organizations in the special operations community, like, anyone know what Navy SEAL stand for? SEAL? Not sleep, eat, and lift, but sea, air, and land. That's kind of all the domains we knew back in the day. You had, the ground pounders had the, anyway, sea, air, and land was all there. But now one of the dominant domains we're experiencing now is certainly space. When I was dating myself, I won't tell you what the year, but I was a Ranger platoon leader, 75th Ranger Regiment. And my platoon got called to actually pilot this new thing called a plugger, which was the kind of early GPS where, is every, you're going to be, we have, how many junior officers do we have here besides you? The biggest fear you had as a second lieutenant in the infantry was getting your platoon lost. You're middle of the night, you've got a little map and a red lens flashlight trying to figure out where you are. It was really hard. Of course now, super easy, GPS, but back in the day we had these things called, you needed 3 space vehicles. I remember, it sounded so cool. We were sitting there with this plugger. You had to have 3 space vehicles to figure out. So won't tell me too many war stories, but boy, how far we've come in just the few decades since I was a Ranger platoon leader. But the space is the future certainly for so many areas, not just the military. We have some amazing panelists. Today we got Kerry Wisnosky. He's the co-founder and president of Quantum Space. Kerry, thanks for joining. He's building the transportation and infrastructure to operate out in geostationary and cislunar space. That sounds really cool. Thanks for joining us. Randy Stiles, Lockheed Martin, friend of a friend of the class, Chris Moran. But he's part of the Ignite team in the Advanced Technology Center, and he works on how humans and intelligent machines team up in the field. And we have Stanford's own Professor Simone. He's a professor of aeroastro here at Stanford and the founding director of the Space Rendezvous Laboratory, science fellow at the Hoover Institution, go Hoover, and the chief scientist and co-founder of Aerodrive. He works on autonomy and rendezvous is the science of this, which is the science that this is built on. So great panel. Of course, we have our own Ernestine, no better moderator to finish strong with. And thanks for coming. Over to you, Ernestine.
I'd like to kick off with maybe we could just talk about what problem in space each of you are most obsessed with solving right now. And Simone, why don't we start with you?
Oh, thank you. So my field of work is really distributed space systems, so systems made of 2 or more satellites that work together. And so if I had to identify problems I'm obsessed with distributed space systems, on one hand, for non-cooperative platforms, I'm obsessed with the problem of translating a high-level mission goal into the autonomy stack that does all the perception, navigation, control, all the decision-making to accomplish that objective. So from high level all the way to the low level and the commands. In the cooperative domain, instead, I'm obsessed with realizing the first virtual telescope with precision control in space that can detect signs of biological activity around the planets orbiting stars.
Randy, what about you?
All right. Well, have some similarities. I'm worried about intent-based control of different assets in space. The DIU made a statement recently that said there is no intent-based control for groups of autonomous systems. And my specific application area, the thing I worry about making sure happens is network communications in space.
What are you obsessed with, Kerry?
What I'm obsessed with is if you think about space today, there's actually about 10,000 satellites in space today. With most estimates are by the end of the decade, there'll be 60,000. Shortly after there will be 100,000. And what's really interesting is a lot of people don't realize once those satellites get into space, they basically are static. They basically stay in the same location over and over and over. And if you went back and looked at it 50 years from now, it'd be in the same orbit. And so what I'm obsessed about is building the capability for satellites to have the freedom to maneuver without regret. And we know, what do I mean by that? Be able to go from low Earth orbit to medium Earth orbit to these other orbits, geosynchronous orbit, even cislunar, and have enough capacity to stay up there. So the Space Force calls it dynamic space operations, where they want to be able to maneuver around and be responsive, or responsive space. And so building the capability to maneuver without regret, that's what keeps me up since I started the company.
Yeah, I'd love to dive into that a little bit more, since quantum space is betting that there's much more variability in orbits rather than today's segregation of LEO, GEO, and then you've also been winning contracts to validate VLEO as well. Maybe talk a little bit more about your vision of space operations long term.
Yeah, I mean, if you think about, again, back to this, I think about what's happened in the last 15 years. Like, as we're sitting here today, in a couple weeks, there's this company called SpaceX. Has anybody ever heard of it? Raise your hand if you haven't. Okay, so, was that a joke, right? Yeah. So you think about it, they're going to go public, and there's going to be a multi-trillion-dollar market. While they're the unicorn, they're just the leading unicorn of a plethora of space companies that have developed over these last 15 years. And why is the space economy now a multi-trillion-dollar market? And it's because 15 years ago, this company called SpaceX, they enabled, they had this thing called Falcon 9 that they put in service. And what did that do? It brought the cost to get to low Earth orbit down to where organizations and universities and people, even outside the government, could actually access space. I call that the first wave, low-cost access to LEO. The second wave was, well, that price went down, what I call the proliferation of constellations. There was OneWeb came into market. We were talking about Planet Lab, right? And now there's Starlink and Leo Lab. Amazon Leo. So that proliferation has created an economy today where, again, there's trillions of dollars of economic value. Thing that, built on this low-cost access to space and all the data services that are wrapped around that. I think about what's going to happen in the next 5-10 years. That infrastructure was never designed to operate in these other orbits, these high-energy orbits, which means you need a lot of kinematic or propulsive energy to get there. And so we're focused on building the propulsion capability to go from low Earth orbit, get there at that low Earth orbit price point, and then take satellites to these other high-value orbits.
Simone, I'd love to talk a little bit more about your work when it comes to satellite swarms and autonomous rendezvous. How do you think about what a formation of small, coordinated spacecraft can do that one big, expensive satellite never could do?
Oh, so many. So basically what we do is to classify distributed space systems according to the distance between the satellites forming the distributed space system, and how well we need to navigate them in order to accomplish the objectives. And so you can create a map and see at one end of the map you find constellation for global coverage, and that's already something that a constellation can do that a single satellite cannot do. So global navigation, global communication. At the opposite end of the spectrum you find rendezvous and docking. That unleashes capability in so-called ISAM, so in space servicing assembly manufacturing. So how to repair a satellite, how to refuel it, how to reboost it, how to deorbit it, etc. So these are capabilities that are enabled by the work of two satellites together. In the middle, you find swarms and formations. Swarms and formation are more exotic concepts, even if they are becoming more mainstream today, where you can form an instrument with an effective aperture for observation, so for imaging, that is much larger than the individual size of the individual satellites. And that unleashes capabilities such as solar, heliophysics, exoplanet science, detecting and direct imaging of exoplanets, planetary science, recovering gravitational field, and digital elevation maps or 3D models of planets in a superior way than what you can do with a single satellite. and so forth. Now, something that people don't know is that we have demonstrated some of these capabilities already in space. Actually, I developed the guidance, navigation, and control system of 5 missions that I've flown in space, employing multiple satellites to do these very things I'm talking about. One of them is currently operational in orbit, which is the NASA Starlink mission, not to be confused with Starlink. Starlink is a bird species. It employs 4 6U propulsive CubeSats that autonomously coordinate the motion, the exchange measurement, they do distributed optical navigation for these kind of applications.
Randy, I'd love to talk also a little bit about your research, given that's focused on humans, machines collaborating, not full autonomy. Like, talk a little bit more about what you think, where's the line, like, when should humans stay in the loop when it comes to space operations?
In terms of what I call intent, there's a prior trend in networking called intent-based networking, where when you're setting up your Cisco system or Juniper system, you have to actually configure a lot of complex things. It turns out there's a lot to learn from that in automating networks in space. And now there is the possibility of actually taking, say, a commander's intent, an operator's intent, and making sure that's reflected in the intent-based networking for satellites. That has not been done yet. That's new work, and that's what we're working on. So that's one thing that keeps me up. Denied communications, all the other things that in the military that they talk about for command and control, no comm, no control. And so that is paramount importance, and being able to reflect what that intent is in logical forms makes it more reliable. But mapping it from natural language and mapping it from what's needed for the specs and what the policies are, and then coming up with a system that translates those policies into logic. That's still a difficult step, and as I mentioned, DIU does not have that for autonomous swarms of any type. That was their statement. And they said the statement was for the Department of War, or DOD. So that's where we're actively working to control networks and automate the use of the networks. And those are not just networks for IP, they're networks for Link 16 and other Ka-band networks and all of that, which is subject to attack. Many people assume that space assets are in space, therefore they're not subject to cyber attack. We saw it different in the Ukraine conflict. Viasat modems were compromising the perfectly functioning Viasat satellites to compromise other modems and take down Ukraine's communication. One of our research folks said to me, well, you don't want to do that. It's like attacking bread. You're going to hit everything else. That's exactly what they did. They hit everything else. Germany, every other place using Viasat. So there are many clever ways of compromising these systems, and you have to adapt, like the PACE system, where you have normal operation all the way to emergency, the E in PACE, and being able to fail back on that, but still get the communications that need to come through.
Yeah. If I think about the next frontier of space infrastructure, I think there's a couple key topics to cover. One being advanced propulsion, and Kerry, for you, given that you guys also just acquired some propulsion assets, I feel like propulsion is that quiet enabler behind almost everything else that we're talking about on this panel. What do you think is the single propulsion advance that unlocks sort of most new missions here?
Yeah. So, I mean, again, the history of satellites, there's essentially 2 types of propulsion, right? There's chemical propulsion, which gets you high impulse, lots of thrust, gives you the ability to maneuver away from debris or away from an ASAT, or maybe if there's some little cat and mouse games going on in space, have the ability to do that, chemical propulsion. But it's not very efficient. On the other class is electric propulsion, right? Things like Starlink, spacecraft. It's got very, very efficient maneuvering capability, but very little impulse, takes a long time to go somewhere. And when we started Quantum Space, we were focused on chemical propulsion, building high energetic spacecraft to provide lots of what we call delta V, ability to change your velocity in orbit. And as we talk to customers, what we were finding out is customers would like to have the ability to be able to sometimes put a lot of energy in and sometimes just be very efficient. So we started doing a lot of mission designs and some planetary missions with NASA. We got an award, one of the Mars sample return studies looking at this problem, looking at some problems on the national security side with the Space Development Agency for the debris model. And it kept coming up to, wow, it'd be great to have both of those. And in fact, there are hybrid systems, but when you have when I say hybrid, you have a single spacecraft that might have chemical and electric, but you've got two separate tanks, two separate fuels, two separate feed lines, two separate controllers, two separate avionics, very much complex. Imagine if you could have the technology to take chemical propulsion and turn it into electric propulsion. And so that way our customers would have flexibility in terms of they get to decide when they want to use what fuel on orbit and stay in orbit for a long period of time. So yeah, as we went through last year, we acquired a company that was focusing on that core IP, we call it multi-mode propulsion, that can take chemical propulsion and turn it into electric propulsion. And we've taken that and we're integrating into our architecture, and it is an enabler. It is the technology that enables you to go change these orbits at the right cost point and unlocks what I would say the maneuvering capability we need.
Yeah. So I guess for cislunar and beyond, are we propulsion limited, or are we power limited, or autonomy limited? Like, what's kind of, where does that real ceiling sit right now?
I would say it's clearly all those things that need to be addressed. In fact, we competed and won a contract from an organization called DARPA, which is Defense Advanced Research Program Agency, which is really always pushing the envelope of spacecraft for us in technology, a program called LASSO. And what it is, it's to build a highly maneuverable spacecraft that can autonomously map the entire lunar surface at really low altitudes above the moon over a 4-year period. And you need autonomy, which is one of the technologies, sensors to do the autonomous, because the distances are very long, obviously from the moon to the ground and making those kind of decisions, as well as, when you're dealing with solar eclipses and the rotation of the moon and Earth, having power is one of the technology areas as well, for sure.
I'd love to talk a little bit more about these autonomous, intelligent spacecraft. I feel like we keep talking about and hearing about intelligent spacecraft that are making decisions in real time. Simone, maybe you could just share a little bit more in terms of what are you seeing that spacecrafts can actually decide for themselves today, and kind of what's still firmly on the ground, especially given the research and work that you've been doing?
Yeah, thank you, Ernestine. I think it's important to clarify what is the state of the art first, because the majority of spacecraft are really playing back machines. So there are scripts, operators on the ground that micromanage these satellites, even doing orbit determination, determining where they are on the ground, do maneuver planning, getting to those telecommands, and then sending the telecommands to the spacecraft for execution. So with my research and also the company that I helped starting with my students, we have made progress into the next level of autonomy, which means instead of being micromanaged, the satellites can already take decisions in terms of modes, transfer a lot of that capability that normally is done on the ground, especially navigation, control, fault detection, isolation, recovery, collision avoidance, bring that to the spacecraft. But still, we are not at the level of what we were talking about earlier, of intent-based autonomy. And so this motivated some of our very most recent research to create a technology based on the autoregressive transformers. You know, some of you know that this is
Decision transformers?
the transformer, the autoregressive
Decision
transformer. Yeah. They are autoregressive transformers, technically speaking, that are the backbone of modern large language models. And they have this capability to encode information of various types. We say multimodal. See text, see trajectory. And so we have trained a pipeline that is able to translate a high-level intent from an operator into all the way to the trajectory, the state, and the control that the algorithms generate as an output to reflect, to be semantically correct and reflect the intent that is desired by the operator. That's really the next stage. However, in space, with the risk aversity, and with the high cost, etc., we need to ensure that such a pipeline is explainable, is trusted, can be certified. And so what we do typically is to take that algorithm and use it only as a warm start. It provides a very good initial guess that then can be provided instead to an optimization algorithm that comes with mathematical guarantees of local convergence so that it can satisfy hard constraints. I think in my case for rendezvous proximity operation, swarming and satellite formation flying, guarantees of meeting those non-convex constraints such as collision avoidance, etc., by refining an initial guess that is provided by an artificial intelligent model.
Mm-hmm. Randy, Simone mentioned the word trust. How do you think about validating and trusting an autonomous system when you can't physically reach it once it's
The
in orbit?
industry is very conservative. When they talk about there are rule-based systems and there are bent wire systems where they control things from the ground, that's very true, and they have a hard time releasing from that. They have to have some prior performance that tells them that it's going to be okay, that it's actually going to execute what it's supposed to do, even when they're out of touch, like on the opposite side of the moon or other places where we don't have a lot of comm. That kind of trust, there are things you can do in terms of logical expressions. Google has worked with Lean and generating Lean proofs for the logical output. Those kinds of systems are useful when trying to do intent-based things. You have something to check against. Mm-hmm. And then as he mentioned, an optimizer that has known properties, and they reduce the search space and get down in the search space and then hand it over to that. There are a number of things you can do with RLVR, verifiable results. Machine learning itself is a form of verification. The reinforcement learning with verifiable results lends itself to this. Decision transformers are another one where there's imitation learning of known algorithms, and then you build on that and can bring in different modes. Those all are fascinating, and there are aspects of control, not just of individual nodes, but of sets of nodes that you need to coordinate, and that's really wide open.
We should talk about deep space connectivity as well, and just the concept of always-on connectivity spanning geo, cislunar. I think that's a huge leap from where we are today. And Kerry, quantum is collecting data in cislunar space. Can you talk a little bit more about what breaks about connectivity and navigation once you kind of leave that more comfortable neighborhood of LEO?
Yeah, I mean, one of the things is the distances are vast, obviously, and the ability to, in fact, it's one of the reasons why DARPA and even other customers, we have a contract with the Space Force to do some what's called situational awareness in cislunar space up around the moon. The Air Force has this theory of competitive endurance, and what that means is General Saltzman has said there's basically these pillars of how they need to operate, and one of them is avoid operational surprise. And so one of the ways you need to avoid operational surprise is to be able first to have domain awareness, to be able to have some sensors to understand what's going on now. In fact, the reality is there's things that are, I mean, it's public information, that are going on up around the moon with particular spacecraft that we're not totally sure what's happening there. And part of it is to be able to have good comms and communications. It's still, relatively speaking, I would say that's an area that there needs to be a fair amount of development. I mean, even when there is an operation up around the moon, basically all the national assets, whether they're civil or military, are sort of put on that asset to make sure, I mean, put on that spacecraft to make sure they can maintain awareness. So, you know, while the frequencies are generally, probably, not generally, but they're similar to the frequencies we're used to operating in at these low Earth ranges, the distances are so, and one of the things that we've experienced over the last couple of years is timing is really critical. So we just take for granted this thing called GPS, which you know, we have everywhere and we rely on for everyday life. That doesn't exist once you get beyond geo, if you will. So, even though you might have good signal, good communication, your timing is fair. In small timing errors really perturbate a lot, very significant in terms of spacecraft maneuvering capability.
Yeah. Who do you think? How do you think about like who's building and owning that backbone?
Yeah. I mean, there are a couple commercial companies, SCN and KSAT, that are basically building larger dishes for those type of applications on a commercial side. And there's a fair amount of, like I would say, fairly new companies that are working on some of the technology. We've heard about quantum computing and things like that being deployed on further spacecraft to kind of mitigate some of the communication challenges. But it's a big effort to still be undertaken, for sure.
Yeah.
Totally agree.
Would love to talk a little bit about on-orbit servicing as well, and Simone, especially the work that you're doing with autonomous rendezvous and proximity operations is really the technical heart of servicing. Like, how close do you think we're able to reliably do all this without a human flying as the final approach?
Yeah, so I like to clarify some, misconception, because I guess that most of the people think that we have this capability. Think that we have the capability to, if I say search and rescue that satellite, for a satellite to actually find, identify, track, approach, characterize the target spacecraft, which might be unknown and non-cooperative and tumbling, then get closer to it, grasp it, stabilize or detumble, and do the rest of the operations that are needed, either to reboost it or to repair it or to the orbit. Well, we are far from having this, comprehensive capability. Especially the problems are with partially unknown and non-cooperative and tumbling targets. The technology has never been demonstrated so far. So we have done steps in the direction of on-orbit servicing with cooperative spacecraft. There have been missions such as Orbital Express in the past. That is, a milestone when it comes to demonstrating the capability of refueling or replacing a battery on another spacecraft, but everything was staged with a satellite that was carried by the mission itself, fully cooperative, etc. We have had other demonstrations. For example, a real milestone in the history of this topic is the Northrop Grumman Mission Extension Vehicle, or MEV, that has prolonged the lifetime of, and is prolonging the lifetime of satellites in geostationary orbit, again, fully cooperative, with a known attitude, known interfaces, etc. More recently, probably the only demonstration of approaching a non-cooperative, partially unknown target, and specifically an upper stage of a vehicle, was done by Astroscale. This is a small company, started in Japan and with offices around the world, including the U.S. So it demonstrated the capability of a mission to approach it in a safe manner, inspect it, collect imagery, then send to the ground for, to recover the shape of that upper stage object. That's it. That satellite has then been parked. It requires several operators in order to use it, and it goes to waste, so to say. So, long story short, we are far from having the technology to approach a non-cooperative tumbling target and do operation on it, and far from the commercial viability of doing that. So there are efforts in the direction of reboost or the orbit as a service that requires autonomy, that requires standards, that requires norms, and all these things in order to become financially viable, and through autonomy basically spread the cost of operators to multiple clients.
Mm-hmm. Let's map this all together, some of the topics we've talked about: propulsion, autonomy, connectivity, servicing. Do you guys think there's a piece of infrastructure that, if it existed tomorrow, would unlock all the others?
One good candidate is in-space compute. There is a mentality in putting spacecraft together that deals with swap, size, weight, and power. Very conservative about the radiation-tolerant processing. And will live in space, and outside of LEO, it's much harsher. In fact, that affects comms too. So very conservative on size, weight, and power. And some with Google's Project Suncatcher and things like that may flip that on its head and say, we have these processors we're putting in space. Now you go figure out how to power them. So that flips that whole swap relationship on it upside down, and that can benefit other things that are in space as well, for autonomy especially.
Yeah, I think of it as I was talking about earlier, low Earth orbit it's a congested space. It really is. It's congested. It's contested. You were talking about cyber attacks. They actually happen every single day on spacecraft. Every single day. It's not a one-off kind of thing, and and it's very competitive. When I say competitive, I mean at a national level. It's not just what the U.S. and our allies are doing; it's what other countries are building in massive constellations. And so, I really believe when you say what's needed to unlock, it's the ability to actually build capabilities in these other orbits at a cost-affordable price. It's still extremely, extremely expensive to go into GEO, MEO, and cislunar space. And the thing that's going to unlock that is, additional launch capacity access. I mean, even today, as we all sit here, SpaceX, they've delivered, and earned the right to basically they own the market, or they own access to space. And even if you think, it's unfortunate what happened with New Glenn just, early part of last week. That sets back the whole space economy, because now there's another alternative that was coming online, and it just shows how hard space really is. And we take for granted the incredible, reliability, if you will, of what they built. And it's going to take a while to get the next capability, but we have to get that to unlock the space economy.
Yeah, I'd like to give a bit of an alternative story by making a parallelism or a parallel with what's happening around us. Think of us. A lot of people in the same room. Think of cars. We have millions of cars on our streets. And we are able to manage them. What is the key to be able to do that? This is a follow-up to what was said, but certainly we have sensing at the edge. Think of our eyes. The importance of having eyes and be aware of our surroundings. For us, for cars, for everything where we have a proliferation of assets, and we have capability to communicate. So that's for us, and less for cars, but we have that. Compute was said, we have intelligence at the edge, and we have sensing at the edge. So to me, the key to make space safe, secure, sustainable, long-term, is really for every spacecraft to be autonomous and have that sensing and that communication capability at the edge, no matter what. It doesn't matter if it's SpaceX launching these satellites. You know, we don't want to rely, for example, on a business case that bets everything on reducing launch costs to below $500 per kilo, for example. That's, for example, how the business case closes for all the AI, you know, data centers. But we want every satellite to bring that capacity with itself, in terms of the compute, in terms of the sensors, the vision, either visible spectrum or infrared, in terms of the communication infrastructure. In a few years from now, we will stare at space and say, well, but it's obvious it should have been all the time, the fact that we have connectivity, persistent connectivity between these satellites in order to be able to manage decisions and do safe actions in space and so forth. So that's
So given all this, maybe in one or two sentences for each of you, what do you think folks in this room should either build, fund, or study?
what I just said.
His lab is hiring, so.
No, but I would like to say something different, because I found that this is very important in my career. It's now like 23 years that I work on the topic of satellite formation, flying swarming, and the wind proximity operation. And I never gave up believing in an idea, in the idea of the distribution and how we can unleash that potential. And now something unexpected in a few years, we've seen that it has become mainstream. So think of build, invest, work on something you believe in your idea that you think will make a change in the future. Because that's a prerequisite for being successful, really believing in the technology you're working on.
Yeah, I mean, I simply think about, if it's in the context of space, that if you take Amazon, and when they started going and building their capability, they had data they were delivering, and then they were like, okay, well, there's this data service model, and then we have to get stuff delivered. And then they were hiring UPS and they were hiring FedEx to deliver their stuff. And then they finally put the business model together and said, no, we can do this all in-house. We can build this infrastructure, this data center infrastructure, where you just click on your phone and you order something and it seamlessly shows up and you don't even think about it. You take that, and to your point earlier, like when we leave now, you have some form of autonomy in your car right now. You don't even think about it. You just get in your car, you push a button, and you might not even be looking. And there's these sensors that are keeping track of, so you feel safe, secure, reliable at the right cost point. And so I use those two examples because what I think needs to happen is we have to build, I keep coming back, we got to do the mirror image of it in space. We have to build a delivery system first. And once we build that delivery system, then the connectivity will just grow over time, using all the sensor technology and thought exercises and AI and ML. It'll be easy to connect the things together once we have the capacity to deliver. So I think it's delivery first, and then connectivity second after that.
Yeah.
Andy,
to build
what are your
the
thoughts?
So it may not seem like it, but space and AI have been intertwined from the very start. I was talking to these guys earlier, in 1999, NASA Ames did Deep Space One, and with the ion propulsion, went out and rendezvoused with an asteroid and a comet. And for part of that mission, it was so far out that they had to turn it over to this autonomous remote agent for Deep Space One. That was at NASA Ames and JPL working together. It's only going to become intertwined more, not less. And the conservative space industry has a verification and validation blind spot. Some of this actually has to be attempted. The feasibility has to be done. So the biggest thing you can invest in, and this is always the crux, as launch gets cheaper, the biggest thing you can invest in is doing your actual system, whatever it may be, including AI, in space. And there's been a number of wonderful CubeSat efforts here that have really developed into great things. There's been the cell phone work at NASA Ames, where they just shot a cell phone into space and on a CubeSat, and it was the controller, it was the sensor system, all the
Well,
miniaturization.
Planet came up.
Yeah, from out of that, that's right. So that kind of thing where you're leveraging what's already available to us, whether it's car autonomy or something, will pay off well in space. That's what I think is to be invested.